Okay, shall I get started? Cool. Okay, welcome everyone to lecture 13. This is the first part of the lecture. We'll talk about service quality in context of memory controllers mostly, and we will talk about other quality of service techniques that we didn't cover in the last lecture. I hope this will be interesting. And I'll start with a brief summary of what we covered in the last lecture, mostly focused on the quality of service techniques. So we've seen DRAM, we've seen memory controllers are everywhere in systems that have long latency memory, right? And we focused on DRAM controllers in the past lecture, but flash, for example, is another memory type that must be controlled. And it also involves tasks that are more complex than what our DRAM controllers are responsible for. And we've seen there are many DRAM types that are specialized for different purposes. And we've also seen that DRAM controller logic is typically large in our systems today. So this is another picture of a more recent chip from Apple M1 processor. And we looked at the functions of memory controllers, and we focused on scheduling techniques. And we touched on quality of service techniques as well. If you remember, scheduling techniques is basically DRAM scheduling. Request scheduling is a request prioritization order, and you can look at many different characteristics of your workload or properties of your requests to decide on what request to prioritize over another. Then we looked at shared resource design. For multi-core systems, we've seen that our systems today have many shared components, and these components are becoming larger over time. And why do we share resources? Because it allows us to improve utilization of resources. When one thread, for example, is not making use of a resource, a specific resource like your DRAM controller or main memory, other threads can make use of that resource. But the disadvantage is if some thread is already using that resource, now you cannot use it as the other thread that demands that resource, and you're essentially starved. And we've seen a type of a problem, inter-thread or inter-application interference, where threads that share the memory system contend for the same resource, and the memory system doesn't know that there are multiple threads running in the system. So the scheduling decisions that we make are thread oblivious. And we've seen that problem manifest in this scenario where we have the MATLAB bullying GCC out of the memory system, essentially. So GCC here in this example, when you run these two workloads in the same system, one of them gets slowed down much more than the other. And the reason for this is basically to understand this, we looked at this picture. We're running two different workloads and two different threads here. One of them is streaming and the other one has a random access pattern. And the reason why, so basically here we will see that streams requests are prioritized over random workload requests. And the reason why this happens is because of our scheduling technique. It prioritizes row buffer hits. In this example, streams requests are prioritized. We only issue streams requests. Basically, we issue a lot of streams requests to main memory before we issue one request from random. You can see some code examples of these two workloads. The streaming workload has a very high row buffer locality. Almost every request of stream is a hit in the row buffer. And the random workload has a very low row buffer locality. So almost every request is a miss or a conflict in the row buffer in the DRAM bank. And they're both memory intensive. And when you run these two workloads on a real system, not MATLAB and GCC, this is stream and random right now, right? They're very good proxies for the MATLAB GCC case. You'll see uneven slowdowns on either workload. And this applies to different types of workloads. You run the stream bully with anything else and it gets prioritized over the other workload, and the other workload basically has much higher slowdown. If you have more cores, the problem gets even worse. Your slowdowns are even more uneven, basically. And this results in an uncontrollable and an unpredictable system. As the programmer, you optimize your workload, assuming that it will work alone in the system. You profile it, you make claims about its performance, but then when I run it with a different workload in my system, your program is slowed down by amounts you have never predicted, basically. This is bad for the programmer and the system designer and many other parties. You've seen this problem manifest in other systems in other ways. So for example, in this picture, we're seeing a multi or many core system, and each core has here a shared resource that could be the L2 cache, for example, or the last level cache in that core. And the attacker workload here is accessing the bottom right core's shared resources using the 8 cores that you see on the left side of this picture. Now it basically occupies every router in this many core architecture. So it basically disallows any other core to access shared resources on other cores. And here we're running a very latency sensitive application in these other cores. And we observe a 5,000 times latency increase. This is not good, right? And these 2 papers talk more about these 2 examples that I gave you. And this is Maslow's hierarchy of needs, and we can claim that quality of service can be a safety and a security problem. I think a better example to this than what I gave in the last lecture is maybe self-driving cars, right? Your car might be running a machine learning routine and trying to recognize pedestrians on the road. But if you have a malicious application running on the same system, contending for the same resources, your car might decide on something that's important too late, and you might get involved in a crash or something. So this is bad. And basically to resolve this problem, we need to control the interference in our systems. And for that purpose, we designed quality of service aware memory systems. We looked at techniques that prioritize requests based on our quality of service requirements in the last lecture. We looked at 3 of them. We looked at STFM, stall time fair memory scheduling, PAR-BS, and Atlas. Today, we're going to cover a bit more of these types of techniques. And if you remember, stall time fair memory scheduling is trying to solve this unfairness problem. And the way it does is it tries to estimate how basically you're running multiple workloads, multiple threads in the same system. You know your thread's performance. So you're trying to guess how its performance would be if it was running alone in the system. And then you can deduce the maximum slowdown or the slowdown that thread encounters running shared in the system. Once you have that, what you're trying to do is you're trying to equalize the slowdowns on each of the threads by dynamically assigning priorities to the thread's memory requests. And that allowed us to increase fairness. So we got the slowdowns of each threads closer to each other using STFM. PAR-BS is looking at a different problem. So this here we're looking at inside a thread. Threads can exploit bank level parallelism, but when we run multiple applications or multiple threads at the same time, the memory controller might end up not exploiting that bank level parallelism. Here's an example. We have 2 requests from thread A and B on the top side. Thread A's requests normally can execute in parallel, right? Because one of them is going to bank 0, the other one is going to bank 1. So you could execute them in theory in parallel, while very close to each other in time. But there's also thread B's requests that I didn't show you here. Okay, yes, this is more clear now. So thread A has 2 requests to bank 0 and 1. And thread B also has 2 requests to bank 0 and 1. But because they arrived in this order to the memory request scheduler, because all of these are bank conflicts, our scheduler picks thread B's requests to bank 1 over thread A's request to bank 1. And this results in both threads to have this large stall time. But if we were aware of intra-thread bank-level parallelism, we could prioritize thread A's request to bank 1 over thread B's request to bank 1. And this will allow us to reduce the maximum stall time for at least one thread. This is how we schedule the requests in the case where we have an intelligent scheduler that's aware of this problem. And the average stall time, we reduced it by quite some margin, right? Okay. And then we looked at Atlas. There are more details on PARBS, obviously, in these papers that you can see in the slide. Atlas's goal is slightly different. It wants to maximize system performance. And we didn't cover this in much detail, and I'm not going to do it today either, but we prioritize, basically Atlas prioritizes threads that get the least amount of service at a given time frame from the memory controller. And you prioritize memory non-intensive threads, and you improve system throughput by doing that. So why does this help? Because memory non-intensive threads, you can imagine them as applications that do a lot of computation in the core without any memory delays. And once in a while, it will schedule it will need to access main memory. And if you serve that very fast, you're allowing the application to make more use of the core's throughput. But if you don't prioritize that request, and if other requests interfere with that and increase the latency, the amount of time that core is not doing anything increases. And proportionally, it's a lot compared to these other threads that are very memory intensive, that access main memory very frequently, right? So you can delay them a bit more because they already need to tolerate that latency that they already have in the system, even if they're running alone. And you can find more details about Atlas here. So this is basically the end of our summary for the previous lecture. And now we're going to look at more of these techniques. So we'll start by some more prioritization techniques, and then we will go into data mapping. I'll give one example to data mapping to reduce interference, and source throttling to reduce interference. So we'll continue with thread cluster memory scheduling. This is a new technique. Here's the problem with existing techniques when this was developed. So you see on the x-axis, weighted speed up as we go right. On the x-axis, we have better system throughput. Our performance increases. As we go down on the y-axis, we have better fairness. So the maximum slowdown induced on any of the threads is very low. Now we will put existing techniques in this plot. Obviously, the ideal point is bottom right corner, right? Because you have almost no maximum slowdown, and you have very high weighted speed up. This is where Atlas is. It's biased to improve system throughput at the cost of basically worse fairness. PARBS has lower system throughput, but it prioritizes fairness. STFM lies somewhere around here. And this is the FRF-CFS scheduling technique that's not considering any quality of service requirements. And this is FCFS. So we say that no previous memory scheduling algorithm provides both the best fairness and system throughput, and we're trying to get to this ideal point here. So why do previous algorithms or scheduling techniques fail? In the throughput biased approach, you're prioritizing threads that are very non-memory intensive, that are less memory intensive than others. Now, this is good for throughput, as I discussed in the previous slides. But when you do this, you're starving the thread that's very memory intensive. Barely gets any of its requests scheduled if you do this, if you have this approach to memory scheduling. You can provide fairness by giving turns to each of these threads. Assume that you have, you do round robin scheduling, you give 10 units of time for each of these threads to schedule their requests to main memory. Now, this is good for fairness because you're not starving any of the applications, you're serving requests equally. But because you're not prioritizing this thread A that's almost not memory intensive at all, because it doesn't get, it's not assigned time to schedule its requests in a timely fashion. So I'll try to explain that in more detail. Basically, the point we're trying to make here is a single policy for all threads is insufficient. And to achieve best of both worlds, we will basically we will split threads into two groups. So for throughput, we want to prioritize memory non-intensive threads. That's hopefully clear by now. And for fairness, we want to shuffle the thread ranking. Ranking means the order which we prioritize the requests from each thread. We will shuffle their ranking. And because they're vulnerable to interference in different ways, we will also, while we shuffle their ranking, we will also not give them equal amount of time to schedule their requests, but we will prioritize one of them over the others based on how nice they are, how vulnerable they are to interference, and how much contention they create. And that will become more clear in the upcoming slides. We will shuffle them asymmetrically, basically, not giving equal amount of time to every one of these memory-intensive threads. So we will group the threads into two clusters. These are all the threads in the system, and you can see the memory non-intensive threads are smaller here, and the memory-intensive threads are bigger boxes. And that's the clustering we're trying to do. So we want to collect the non-intensive threads in one cluster and the others in the other cluster. And once we have these two clusters, we want to prioritize the non-intensive threads over the intensive threads. This is good for throughput. And we will apply different policies to decide which requests to schedule inside each cluster. And at a high level, we want to give higher priority here in the non-intensive cluster to threads that are less memory intensive, as you can see here. And we will do some sort of shuffling in the memory intensive cluster. Okay, so so how do we cluster threads? We sort them by their MPKI. This is how many requests. You can think of this as how many requests they schedule to main memory every 1,000 instructions. And we will basically have a cutoff point somewhere in the slide, somewhere on the slide, to determine which threads belong to the non-memory intensive cluster and which threads belong to the memory intensive cluster. Basically, it's a function of the total memory bandwidth usage of all threads that we have running in the system, multiplied by a parameter alpha. It's called the cluster threshold. And you can see here, by assigning different values to alpha, you can prioritize fairness or throughput. So if alpha is 0, every one of your threads is memory intensive. And if alpha is 100, everything is non-intensive, considered non-intensive. So if alpha is 100, for example, you're prioritizing the lowest memory intensive thread over everything else. So you're optimizing for throughput completely, and you're not considering fairness at all. If it's the yes. Yeah, that's a good point.
How would you know in advance the miss per kilo instructions of each thread?
Yeah, that's a good question. So we don't know. We profile them. I'll come to that in the next slides. Basically, we run the application. We have a quantum-based approach. Basically, we're profiling the application for some time, and then we enforce in the next quantum of time. We enforce the scheduling rules that we determined. Yeah. Okay. Okay, so once we have these two clusters, we prioritize the non-memory intensive one over the memory intensive one. And this increases system throughput. And it does not degrade fairness, because fairness is really a problem inside the memory intensive cluster. This is because non-intensive threads are light. They rarely interfere with intensive threads because they have one request every once in a while in the memory request buffer, right? And once you schedule it, it's gone. It's not interfering anymore. Yes, so I think I talked about this already. And let's go to the intensive cluster. So how we do shuffling. We want to periodically shuffle these memory intensive threads so they get priority over others in certain regions of time. And this will increase fairness, but this is not good enough because they have different tolerance to being prioritized over others. So I'll explain this in the next slides pictorially so it will become more clear. If we give them equal turns, they don't get same slowdown basically, because these are different threads with different memory access patterns. So we will look at this over an example. We have a random access thread and a streaming thread. They're both very memory intensive. So which one is slowed down more easily? If you prioritize random access, streaming gets slowed down by 7 times. If you prioritize streaming, random access gets slowed down by 11 times. Why? Because random access is more easily slowed down. So you have this sort of an access pattern when you're running the random access workload. You have multiple requests going to different banks, and you can parallelize them if this is running alone in the system. And it has high bank level parallelism, basically. When you run streaming, it's accessing the same bank, same row, but different columns. It's streaming through the activated row. It cannot, basically, because all requests are going to the same row, it has high row buffer locality, and it doesn't have bank level parallelism. So when you run them together, your random access workloads will get stuck. One of the requests that target the same bank as the streaming workload will get stuck behind those streaming workloads requests. And here, the random access workload is more vulnerable to interference than the streaming workload when you run them together. So what do we do then? We quantify how nice these threads are. So we have this niceness scale. As we go left, the thread is nicer. As we go right, the thread is less nice. As you go left, you have more bank level parallelism in your thread. So this is more vulnerable to interference. As you go right, you have higher row buffer locality, and you cause the interference yourself. And we determine how nice threads are based on these two statistics, two properties of the threads. And what you want to do is you want to give more priority to the nicer threads. So that's how you do asymmetric rank shuffling. You give, over the same amount of time, you give more priority to nicer threads than the other threads. If all threads are equally nice, you can just do random shuffling, like without any priority, like you can do it symmetrically, basically. You can do it round robin. Okay, so this is going back to that profiling answer that I gave. So you have a quantum-based operation. You profile the application in one quantum. You monitor some properties of your workload, such as memory intensity, bank level parallelism, and row buffer locality of your workload. And then in the next quantum, you will enforce this ordering that you came up with. And the shuffle interval here, for example, is in the order of 1,000 cycles. So you're shuffling the memory-intensive clusters, threads, priorities. So this is the overall scheduling algorithm we have. We start with the highest priority is the highest rank requests, but you prioritize the non-intensive cluster over the intensive cluster as well. And inside the non-intensive cluster, you prioritize requests coming from threads that have the lowest memory intensity for throughput again. And in the intensive cluster, you do a rank shuffling, asymmetric or symmetric, depending on the distribution of niceness across your threads. And then you prioritize row hits like FRS CFS, and then the oldest request. So we also just investigated the cost, chip area cost of implementing this scheduling mechanism, and they found that it is less than 4 kilobits of storage, requires less than 4 kilobits of storage, and it's not on the critical path, meaning that you could integrate this into your memory controller, and you wouldn't need to reduce your clock frequencies. Okay. And here we will compare it to previous work. We've seen all of these. This is the same plot I showed you earlier. So we'll put these prior works, we'll distribute them over this plot. And TCM lies over there on the bottom right corner, as bottom right corner as you can get. So this means basically you have, by applying a heterogeneous scheduling policy, you provide best of fairness and system throughput. And you can also configure the cluster threshold, adjust the cluster threshold to get a nice trade-off between fairness and system throughput. So if you, I've talked about this before, right? So if you make your cluster threshold 100%, you're essentially prioritizing for throughput only. If you make it 0%, you're only shuffling based on niceness of the threads. So you're fair. And the operating system also can play a role. Basically, it can tune the cluster threshold to trade off between fairness and throughput, as I described. And it can assign weights to threads. So instead of rank shuffling, for example, you can rely on the OS to assign weights, importance to threads based on system level agreements that you have in that system. Okay, so to conclude, we've seen that no previous memory scheduling algorithm, when TCM was published, provided both the highest system throughput and fairness. And are basically because they use a single policy for all the threads. And by grouping threads into two clusters and prioritizing the non-intensive cluster over the intensive cluster, we optimize throughut. And shuffling priority in the non-intensive cluster, we optimize fairness. And we have this asymmetric shuffling that between nice threads that improve fairness even more. We conclude that TCM provides the best system throughput and fairness when the time it was published, I guess. So the upside of this mechanism is it provides both high performance and fairness. And you can cater the needs for different types of threads, like latency sensitive threads and bandwidth sensitive threads. Latency sensitive threads are in the non-intensive cluster, hopefully. It's relatively simple compared to, for example, SDFM, which needs to look at many statistics over execution time, over the execution of your workload and do a lot of calculations based on those statistics to make scheduling decisions. And now the downsides could be, how do you scale this to larger buffer sizes? How robust is your clustering and shuffling algorithms? Can they really work well for all sorts of applications or combinations of applications? And arguably your ranking scheme is still too complex. And I leave these weaknesses as exercise to you. Please read the TCM paper for more details if you're interested in it. Okay, do you have any questions for me? Oh. Cool. Now we're going to talk about the blacklisting memory scheduler. So this paper argues basically this is how we do intelligent scheduling in the context of quality of service, right? We look at our threads, we monitor their execution statistics, execution characteristics, and we rank them based on the priority we want to apply. And then we enforce this ranking in the memory controller and prioritize requests based on that. Now they investigate these schemes and they find that this sort of ranking in the memory controller increases the critical path latency. That means you cannot, your frequency that the memory controller operates, the circuit operates at, must reduce, must become smaller. And this full ranking also has huge area overheads. It helps us improve performance and fairness, but they're costly to implement, basically. And then we have this nice radar chart that shows us how fair, how high performance, and how simple existing mechanisms are. So this is the ideal outline you want to be in. Right? You're most fair, most high performance, and most simple. So FRF-CFS is very simple, but it's not very fair or high performance. And this is because it's not aware of the applications running in the system. And PARBS we will see how PAR-BS, Atlas, and TCM look like on this plot. So this is PAR-BS. It's very fair. It's not as high performance, but it's very difficult or complex to implement. This is Atlas. It's very high performance and simpler compared to PAR-BS, but it's not fair. It's completely just optimizing for throughput. And TCM is, more fair than Atlas, as high performance as Atlas, and slightly more fair than Atlas. Sorry, slightly more difficult to implement than Atlas. These are application aware. I'm sorry, I have animation bugs in the slide. Application aware, they apply the ranking schemes. That's why they're not very simple to implement. And the question in this paper, the problem we're trying to solve is, basically, do we need to sacrifice simplicity to maintain high performance and high fairness? And the solution we have in this paper basically does not sacrifice simplicity for high performance and fairness. And we'll see how that works. So we make two observations. The first one is, it's enough to separate applications into two groups rather than do a full ranking of all applications running in the system. So monitor your applications. You don't rank them. You have two groups. The first group consists of applications that are vulnerable to interference. The other group is the applications that cause the interference. So this is close to this niceness metric I described, right? And you group your applications or your threads according to this clustering. You prioritize the vulnerable group over the interference causing group. This is a lower complexity compared to ranking all of the threads. And it also has lower slowdowns than ranking. But how do you classify applications into a group, right? And the second observation is, to serve a large number of consecutive requests from an application, it will cause interference. So you want to group applications with a large number of consecutive requests and as interference causing. This is similar to the streaming workload that has a lot of row buffer hits, but also has a lot of consecutive requests in the memory scheduler, in the memory request buffer. You want to deprioritize these by blacklisted applications that are causing the interference. And you don't want to deprioritize them forever. You want to clear the list periodically. And the benefits of this is it's lower complexity, lower implementation complexity. And it also results in low unfairness. So this is, again, the radar chart. This is where the blacklisting scheduler is the red. Basically, it's indicated by the red lines. It achieves highest performance. It's close to fairest. And it's close to simplest also. Again, yeah. It's not the most simple, most fair, or most high performance. So it's highest performance, but it's not the most fair or the most simple to implement. But it's very close to the most fair and the most simple to implement previous scheduling mechanisms. And here's how it performs compared to prior work. Again, this is the same plot I've shown you in TCM. So it's best to be in this bottom right corner. These are where, so this, let me animate it again. FRF-CFS is here. FRF-CFS cap and PAR-BS are over there on the right. And these are TCM and Atlas. So Atlas provides a higher performance at the cost of unfairness, right? And this is where the blacklisting scheduler is. It's 5% higher performance than TCM. This is the state of the art. And it was the state of the art back then. And then 21% more fair than TCM. It achieves the highest performance, and it has a nice balance between performance and fairness. Now, this is what you're looking at is the complexity of the memory controller design in terms of scheduler area in square micrometers, and the critical path latency is on the x-axis. So the ideal point here is as close to 0 as possible. And FRF-CFS is very simple. FRF-CFS cap is also very simple. Cap is basically limiting the number of consecutive row hits a single row can sustain. So basically, if you have a streaming workload, you can set your cap to 16. If you have 128 cache lines in the row, After you read 16 of them, you're deprioritizing that request. You're allowing other requests to access the bank. That's the difference between FIFCFS cap and FIFCFS. The difference is very simple. And here you see other mechanisms laid around in this plot. And the blacklisting scheduler is very close to ideal here. It's 43% less area than TCM, and 70%, it induces 70% smaller critical path latency. So we say that blacklisting reduces complexity significantly. And for more details on blacklisting memory scheduler, I refer you to this paper. Okay, there's an even longer version at this time. Again, I didn't go into details, but if you're interested, please read these papers. So we're gonna look at a different class of interference now. Now, do you have any questions about Bliss? Nope. Okay. We're going to look at interference in multi-threaded applications. So we've been looking at multi-programmed applications until now. Now we're going to look at a single application running multiple parallel threads at the same time. Professor Mutlu has more lectures that cover this single topic in more detail. You can find them here. And let's just get started. So threads in a multi-threaded application can be dependent on each other, as opposed to threads from different applications. They don't really need to synchronize between each other, right? They're different applications. These ones need to synchronize with each other using locks, barriers, and so on. And basically some threads, as you will see, will be on the critical path while the others are not. This will become more clear in the next slides. Even inside a thread, some code segments may be on the critical path and some are not. Basically, some parts of the code the thread is executing is on the critical path. And once the thread exceeds that point, it's no longer on the critical path. Critical path in the sense that it's like the workload's throughput. So this is an application that's running on multiple threads. And for highest throughput, you want all of these threads to perform very fast, right? But some of them don't. So let's look at critical sections first to understand this problem better. These critical sections enforce mutually exclusive access to shared data. So this is an example. Each thread in your application is executing this code block. They do some compute. This is the normal section, let's say, of your program. And then they acquire a lock, meaning that only one, for example, thread can execute what's the code block inside this lock. This is the critical section. And yeah, only one thread can execute at a time. And on this diagram, you see an example execution of two threads running the same code block. Thread 2 here is executing the normal code block and takes the lock and goes into the critical section, while thread 1 is slightly late, so it didn't acquire the lock. And now it's waiting for the lock, and it's not doing any useful computation in this red dotted line part of the diagram. The key idea will be basically, if you know when the thread 2 is executing this critical section, if you can somehow accelerate that, thread 1 will acquire the lock earlier, right? This is the key idea we're going to use. Yeah, contended critical sections, in this example, it's critical section C, will make threads wait. The other thing we're going to look at are barriers. These are synchronization points for threads, multiple threads to stop at before the next part of the computation can start. So here, for example, we have multiple threads executing the loop, compute loop 1, and then they all have to finish before they can start executing compute loop 2. So here's another diagram that shows you the same bottleneck, essentially. So T1 here finishes executing loop 1 earlier than T2. T2 gets to the barrier late. Because of that, T1 couldn't do any meaningful computation here. And we want to get this barrier where it meets the line, like timeline here, towards the left. We will try to accelerate T2. But basically, we're going to only focus on techniques that allow us to identify these critical sections and bottlenecks, essentially. And the way to accelerate them in different contexts are going to be different. So if you're looking at memory controller, if you can identify the bottlenecks in the memory controller, you can prioritize the bottlenecked threads requests to make the thread execute faster. Or if you have asymmetric multi-core processor systems where you have smaller and larger cores can execute essentially at a high level faster, and smaller cores execute things slower. You want to execute the critical threads in the larger cores. You want to reschedule things. Okay, let's look at stages of pipeline programs. So we will divide loop iterations statically into code segments, and we call each of them stages. So we have 3 stages in this loop, and these stages execute on different cores. In between these, we will have barriers to synchronize the threads. So basically, A takes some input, does some computation, and outputs something. That output goes to thread B. And for that output to be valid, they have to synchronize. And this is what the execution timeline looks like for these 3 threads. You can see thread 1 and thread T is suffering from thread B's low performance here. If you could execute thread B faster, you could improve system performance for your workload. Okay, so these are things I discussed. But how do we schedule requests of interdependent threads to maximize multi-threaded application performance? We will look at one idea. This idea estimates limiter threads that are likely to be on the critical path, and it will prioritize its requests. And for non-limiter threads, it shuffles priorities. It uses ideas from the paper from TCM that I described earlier. And it also uses a hardware-software cooperative limiter thread estimation technique. It looks at threads executing most contended critical section, the slowest pipeline stage, and the thread that falls behind the most in reaching a barrier. And for this, the OS inserts some hints into parts where the threads reach the barrier and so on. And this is a pictorial description of the technique. So we have 4 threads executing 2 critical sections and synchronizing on a barrier here on the right-hand side of the diagram. Now, if you look at the critical path, you'll see that it's this. If you could reduce the execution of any critical section on this critical path, you improve system performance. So how do you do that? You have, again, 2 stages. You're trying to profile your workload, and you're trying to identify the most contended critical section. So you spend some time on doing that, and you found that critical section 1 is the most contended one because it was executed. All threads went into critical section 1. They all want to acquire the lock. Once you do that, once you decided on the most contended critical section, now you know which thread is executing that critical section, and you're trying to prioritize that thread's request so that it finishes executing the critical section earlier. And by doing that, by reducing the execution time of that section even slightly for every thread, you can bring the synchronization point earlier in time, and you've accelerated your workload essentially. Again, this can be done in the memory controller, if you know that the bottlenecks are due to, or if you can identify the parts of the bottlenecks that originate in the memory controller due to memory controller's poor scheduling decisions, you can prioritize threads and accelerate your multi-threaded application. You're reducing the critical path. Yeah, so this is the high-level idea. So this improves the performance of multi-threaded applications, and it provides a mechanism. The paper provides a mechanism for estimating these limiter threads. And yeah, it opens a path for slowdown estimation for multi-threaded applications. And more work builds on this to make better estimations. This work doesn't address the case where you have multiple multi-threaded applications running at the same time, but future work building on this does. So the other downside is limited thread estimation can be complex, and this bottleneck identification and scheduling, or BIS paper, it provides a hardware-software co-design that makes it easier for hardware to identify the bottlenecks. Again, I won't go into details of those. So this is the paper I gave the high-level idea of. You can read this for more details. And you can refer to Professor Mutlu's lecture on parallel application scheduling. This is the BIS paper. This is the hardware co-design, software hardware co-design paper that allows us to more easily identify critical sections. And this is another paper that's building on top of those two. So it's basically the key idea here is running multiple multi-threaded applications at the same time. You don't know how to determine the critical section in that case. And the paper considers the acceleration expected for that thread when you run it on a large core. This is again the asymmetric multi-core processor systems that I described. That's the context. You estimate that thread's performance as if it was running on a large core alone, and you try to estimate the performance loss due to interference, and that allows you to generalize this critical section acceleration to multiple multi-threaded applications. Again, I won't go into detail, but yeah, read the paper if you're interested. And more lectures on bottleneck acceleration. We will look at memory scheduling for heterogeneous systems. Again, quality of service. You remember our systems are this slide that shows a very heterogeneous system. The problem we're trying to solve here is how we allocate resources for to heterogeneous agents here, the GPU, hardware accelerators, CPUs, to mitigate interference and provide predictable performance. And yeah, this is a picture to show that our systems that we use today are very heterogeneous as well. In an Apple M1 CPU, this laptop CPU, we have small and large cores. We have neural engines, ML acceleration, machine learning accelerators, GPUs, and many other components that are not visible here. There are, again, more detailed lectures on heterogeneous system scheduling, Professor Mutlu's, and more details about heterogeneous computing systems themselves, not just scheduling for them, in this link. I won't go too much into details of this few papers that I go over here, but stage memory scheduling is one example. The problem here is in a heterogeneous system, you don't only have the CPU schedule requests. You have the GPU that's going to request many cache lines at the same time from main memory. And what happens then is you have you have tons of requests coming from the GPU, but only a few CPU requests coming from the CPUs. So with the memory request buffers that we have today, maybe the size of 64 requests, you cannot look forward into the future enough to understand the locality or memory access patterns of the CPU requests, because your request buffer is dominated by requests from the GPU. Now, this paper develops a new memory controller design that allows us to implement very large memory request buffers. And the challenge of implementing large memory request buffers is complexity, and it basically designs a decoupled memory controller design, decoupled in the sense of functionality. So one part of the memory controller now just deals with grouping requests, and the other part deals with scheduling requests. And this allows you to implement very large buffers at low cost. That's the problem this paper deals with. Dash is, or deadline-aware memory scheduler, is trying to make performance guarantees, or trying to provide predictable performance in cases where you have hardware accelerators with that send memory requests with deadlines. Deadlines meaning that memory request has to be issued before that deadline. And in a heterogeneous system where you have these accelerators and the CPU requests, there are two problems. First, the hardware accelerators often misses the deadline. The request often miss their deadlines because the memory controllers that we have enforce priority, prioritize the hardware accelerators request only when you're very close to the deadline. And at that point, you have too many requests to schedule. So some of them will miss their deadlines. And prioritizing them at that point also causes interference for CPU requests. This paper comes up with a new mechanism that dynamically prioritizes hardware accelerator requests over time, not just immediately before the deadline. And by doing that, it also reduces interference to CPU for CPU requests. This is something I briefly covered in the previous lecture as well. There's also CPU I/O interference. Here, you have now I/O agents like DMA engines, direct memory access engines, that, for example, fetch data from your storage device, put it into main memory, that interfere with CPU requests. Because the bandwidth requirement of that DMA engine is almost as high as your the memory bandwidth that you have. This is a new DRAM design. This paper has a new DRAM design that doubles the memory bandwidth, but at very low complexity, let's say. And I'll leave it at that. And by doubling that, you partition half of the bandwidth now to CPU requests and the other half to I/O requests. And you reduce interference. Okay, this is the almost the last part of the lecture. So we're going to look at predictable performance. Actually, I'm going to skip this very quickly. Here we're dealing with how to allocate resources for heterogeneous agents, mitigate interference, and provide predictable performance, again, in the same system. Professor Mutlu has more lectures, more detailed lectures on this topic. And we're going to look at this paper, Fairness via Source Throttling, in more detail a bit later. These are the papers that deal with this topic, essentially. So I'm going to flash these papers to you and move on to the next part, the final part of our lecture. So we're going to look at now these these techniques that we didn't cover yet. Data mapping, and I'll give you examples on data mapping and core source throttling. And we're going to see some works that deal with application and thread scheduling. More lectures from Professor Mutlu. Okay, we're going to start with memory channel partitioning, so we don't have too much time left for me, but I'm going to cover these then. We're going to continue with the next part of the lecture. So memory channel partitioning is a very simple idea. Back then, modern systems have multiple memory channels. So now we have multiple memory channels, yes, but back then it was not a thing. It was becoming a thing. So since we have multiple channels, why don't we map data in a way that we reduce interference across multiple programs? So here you have two applications running on the same system, and they're assigned to the same memory channel. Parts of their data is assigned to the same memory channel, so they're interfering with each other. You could split their data to channels, and there would be no interference, right? This is the key idea we're trying to make use of. So our goal is to eliminate harmful interference between applications. And the basic idea is to map the data of badly interfering applications to different channels. And we want to separate low and high memory intensity applications from each other and low and high row buffer locality applications from each other. So how do we do that? First, we have two key insights. The first one is high memory intensity applications interfere with low memory intensity applications in shared memory channels. This is probably clear to you already from the previous papers. So this is an execution timeline again. Red app and blue app are accessing their data that is not partitioned yet across channels. So their data exists in both channels. But the red app is very memory intensive and the blue app is not memory intensive. And if you do this ordering of requests, you can see that the blue app's request is delayed a lot. It's serviced at time unit 4. What's going on? Okay. And if you partition their data to two different channels, the Blue apps request now is serviced much earlier, right? You saved a lot of cycles, basically. Okay, so we want to map data of low and high memory intensity applications to different channels. But that's not enough, because high row buffer locality applications also interfere with low row buffer locality applications. So here's an example. You have multiple requests from the Blue and Red apps. And if you service them in this order with conventional page mapping, you see that R3 Blue apps request 3 takes a lot of time to be serviced. If you consider row buffer locality and separate the application's data to different channels based on that, you can reduce this interference. You can service both applications much faster. So we want to map data of low and high row buffer locality applications to different channels as well. To do that, we will profile applications and classify them into groups, and then partition channels between application groups. And we will assign a preferred channel to each application. And when we're running the workload, we're going to allocate application pages to that preferred channel. This will require data movement, as you can maybe imagine right now. The profiling step is done by the hardware, and the system software deals with the rest of the steps. And it's also similar to this quantum-based or interval-based operation that we described for TCM. So in the current interval, we're profiling the application to gather some statistics and classify them into groups and partition channels between groups. And in the next interval, we will enforce the preferences that we came up with for these applications. We make some observations in this paper. So first, with applications that have very low memory intensity, rarely access memory. We have seen this in the previous works as well. Dedicating channels to them results in precious memory bandwidth waste. So this is going back to the example, Red application, Blue application. Blue application had only one request. Red application had many requests. So if you do that, the channel where Blue applications requests are scheduled is basically not utilized almost all of the time. So you don't want to do that. But you want to prioritize them also. And they don't really interfere with other applications because they're very low memory intensity. So you always prioritize the low intensity applications in the memory scheduler. And you partition workloads that can interfere with each other across channels. And the hardware cost is relatively small. You need some profiling counters in the hardware because hardware deals with profiling. And you don't modify the scheduling logic at all. You're just partitioning data across channels. That's something the OS can do. And it basically induces 1.5 kilobyte storage cost for a 24-core 4-channel system. And another technique they develop in this paper is integrated memory partitioning and scheduling. This is sort of best of the both worlds approach. You associate a single bit to each request, and the memory scheduler prioritizes based on this bit. This is to prioritize the low memory intensive applications, for example. And the performance of this approach looks like that in this plot. You have normalized system performance on the y-axis, so the higher you go, the better. And we have the previous scheduling techniques that I described here. And MCP provides 1% higher normalized system performance over TCM. That's the state of the art. And integrated memory partitioning and scheduling improves the memory performance improvement by 4 more %. So it performs better than any previous scheduler at lower hardware cost. This is Professor Mutlu's example of bad channel partitioning that you can see in the Cloton airport if you're coming from terminal E or going to terminal E. This is before you take the train that goes between terminals, and no one's using the other channels here, the other escalator channels essentially. And some people here want to maybe go faster, but they cannot because it's contended. This is a good example, no? Okay, so something about combining multiple interference techniques. Combining these techniques can mitigate interference more than a single technique, and we have seen that with IMPS. The key challenge is deciding what technique to apply when, and partitioning work appropriately between software and hardware. And these are the advantages and disadvantages of MCP and integrated memory partition and scheduling. The upsides are the hardware is very simple because we didn't change the scheduler at all, right? We just added some profiling counters. We combine multiple interference reduction techniques, and we've shown their benefits. And we can provide performance isolation across applications that are mapped to different channels. And you can maybe extend this general idea of partitioning to smaller DRAM components or smaller DRAM granularities like banks, subarrays, etc. Now, the problem is, if your workload changes behavior after you profile it, it's difficult for you to react. So you profile the workload to be, let's say, not interfering with that another workload that you have running. And immediately after your profiling step, it started interfering with that application. Now you cannot do much until the next interval comes. And when the next interval comes in, if you decide to move that application to another channel, now you have to move the pages of that application to the other channel. So that involves a lot of data movement, and it restricts your benefits. You don't really want to move data, and you don't really want applications to change behavior that often, but we know that's not the case, right? There's more on memory channel partitioning in this paper, and we'll cover one last technique and then summarize and end lecture 13A. So this is the source throttling approach. This is yet another approach to maintaining quality of service. The key idea is to manage interference at the cores. That's why we call it source throttling, not at the shared resource like the memory controller. And we dynamically estimate the unfairness in the memory system and feed this information to a controller. A controller in this case is not the memory controller. This is controlling the core. And we throttle cores, memory access rates, based on this dynamically estimated unfairness metric. And this is similar to how STFM, stall time fair memory scheduling, does it, but at the source level. So if unfairness is higher than a software specified target, we will throttle down our cores and throttle them up when unfairness is not a problem anymore. So how do we do that? We have two components. It's again interval-based mechanism. We estimate the runtime unfairness in hardware. So basically, we're trying to see which application is slowing down which other application. And then the throttling part comes in. So we adjust how aggressively each core makes requests to main memory, to the shared resources, not just main memory, sorry. And we throttle down the request rates, of course, that interfere with other cores. And the way you do that is we can limit miss buffers. This is miss status handling registers. So basically, these are buffers that we have in various levels of the cache to maintain data about, maintain information, metadata about requests that are outstanding. So we missed that request in that level of the cache. Now we associate a status register to hold various metadata about that request. If you limit the number of those registers that your application can use, you essentially limit the number of requests it can inject to the rest of the system. And this is the interval-based approach. So you estimate the slowdown of each core on each other core in one interval, and you find the app with the highest slowdown, find the app with that causes most interference for this slowest application. You give this information to your controller, dynamic request, that employs dynamic request throttling. And if your unfairness estimate is larger than the system-defined threshold, you throttle down the interfering application. So how do you do that? So I'll describe how dynamic request throttling works. The goal is here to adjust how aggressively each core makes requests to the shared memory system. And yeah, I described this. So basically, you're controlling a number of MSHRs, miss status holding registers, that an application can occupy, and you control how frequently they're allowed to inject requests. So this is an example. This is the throttling. This is showing the throttling level on this first column for each application, and the associated number of MSHRs and the request injection rate for that throttling level. So here, basically, if you're not throttled at all, you can use all MSHRs, and you can inject requests to shared resources every cycle. If you're throttled by 10%, throttled down to 10%, you can only occupy 12 MSHRs, and you're not allowed to inject requests every cycle. You can only inject a request every 10 cycles. And if some other core wants to inject requests at that cycle, you're also probably deprioritized. Yeah, so system software support, we can specify different fairness objectives from the system software. You can have a target maximum slowdown, or you can have target slowdowns for every application. And your controller tries to match these limits, basically. And your operating system can assign weights to threads. So you can, as the operating system, you tell the hardware controller, basically, throttling this application is more important than the other, for example. Okay, key takeaways, basically throttling alone provides better performance than a combination of smart memory scheduling and fair caching technique. I'm not showing you the results in detail, but these are the takeaways. This is because if you have those two techniques implemented in the same system, sometimes the fair caching techniques, the decisions that fair caching technique makes contradicts with the decisions that your memory controller makes. So they have to cooperate, basically, and they're not cooperating. We also see that source throttling alone or smart resources alone cannot provide the best performance. So combining them likely is better. The advantages of this technique is it's easy to implement. You don't need to change the memory scheduling algorithm. And it can be a general way to handle shared resource contention, throttling things at the source, basically. It doesn't have to be just the core, right? It can be GPU or a hardware accelerator. You can reduce the overall load in the memory system. You can allow for more applications with higher priorities to access that shared memory system. The disadvantages are you need to estimate slowdowns, and it's this difficult since STFM. It's the same problem. And your thresholds, you have to optimize them. And these are heuristics, right? And heuristics are difficult to optimize. You can accidentally lose too much throughput by throttling applications too much. And overall, finding a good, trade-off point can be difficult. And this is the full paper, Fairness via Source Throttling. There are works that build on this, but I'm not going to cover them. Source throttling in context of networks, for example. And I'll briefly cover this. So this is application to core mapping policies to reduce memory system interference in multi-core systems. This is a different technique, different class of techniques for maintaining quality of service. You have a many core system, and some cores are closer to the network chip, for example, than others, so that they can have faster access to network, higher throughput access to network. Some cores are closer to the memory controller, and they have faster access or lower latency access to main memory. And here, the work is trying to deal with application mapping such that cores that or workloads that would interfere with each other, for example, are placed in different parts of this multi-core or many-core chip. They access different memory channels, for example, so they don't interfere with each other. And cores that require high throughput network are placed next to that high throughput network card, or the interface to that network card. And latency sensitive workloads are, for example, placed closer to the controller. And this is architecture aware DRM. This is similar to the previous work, but in a different context. It's a virtualized environment, and you're trying to distribute applications to your cluster in a way that they don't interfere with each other in the same shared resources. Okay, we'll summarize and end this part of the lecture. So we looked at many interference reduction or controlling techniques. We classified them into 4 groups. And I think it would be best to combine them all. And we have seen techniques that combine a few of them, and they perform better than using a single technique, right? There are mainly 2 approaches. You either have smart resources or dumb resources. And you can use scheduling techniques, prioritization techniques in your scheduler. You can throttle sources, or you can partition dumb resources to your workloads in a way that reduces interference. And we have seen a bunch of these. And we also hinted to the fact that combining them probably is the best or the most powerful approach. Basically, again, going back to the problem, if you have a quality of service unaware memory, you end up with an uncontrollable and unpredictable system. This is bad for many things like programmer quality of life, I would say, and system level agreements that, as an organization, you provide to your customers, for example. And providing quality of service awareness will improve your performance, predictability, fairness, and you will allow multiple sources to utilize the memory system in a fair way. We discussed many techniques to do these, and I think we need, well, at least Professor Mutlu thought when he prepared the slides, many new research ideas to for integrated techniques and closing the interaction with software. We didn't cover many techniques also. These bullets list them. So for example, you have the same concept, quality of service, in conjunction with prefetches. Prefetches are something Rahul is going to cover. Maybe he's going to cover some papers about quality of service as well. We'll see. And many others. And you can find more details on these techniques in the videos that I have in the slides. In the future, we can have potentially more quality of service techniques in heterogeneous SOC systems. We can have combinations of these techniques, different combination of these techniques. Maybe we can use machine learning techniques also to manage these resources in a way to improve quality of service. And we could have real prototypes. Actually, we're working on one of them. We can have real prototypes that allows us to test, evaluate these scheduling techniques, real in the sense that it's actually a real hardware chip or a device. Okay, that concludes my part of the lecture and quality of service in general. Okay.
Push, I guess, yeah. Okay, so I guess this is, but it's better to cover anyways. About threads, are we referring to processor cores, virtual cores, or software threads of an operating system?
Yeah, so maybe I use them interchangeably, but I mostly refer to applications or software threads.
So that means that we provide thread IDs for memory operations, basically when we do thread-aware scheduling.
Yes, yes. I guess you can do it, and you can provide hardware threads also in that case, right? But the meaning of that hardware thread will change when you schedule a different a software thread to that hardware thread or core. So you have to take that into account if you don't want to have very large thread IDs. Yeah. Okay. Okay, we will take a break until 14:40. Yeah, past 11 minutes, and we'll meet again. Thank you.
think it's working, right? Can we see whether this is good in Zoom? It's fine. Hello. You can hear me, right? Okay, perfect. I can hear an echo. It's working. Okay. Okay, so yeah, so let's welcome to the next part of the lecture. I hope you are still alive now. Let's see if we can make it more alive. So this part would be based on prefetching. And how many of you have taken the DDCA course? Anyone? Okay, so maybe some part of the concepts are not so familiar with you, but I hope I can send you the pointers, right? So at least to look for the parts in the DDCA lecture that's kind of relevant to this topic, right? So wait a sec, something is not working. Nice. Now it's working. Okay, perfect. So I'm Rahul. I'm a PhD student in Safari Research Group. So this is my website. So you can see, the other works that we have done on this direction, especially on prefetching and, cache replacement policies and stuff. So that's my email address. If you're, interested in working any of on these topics, then just, that's the best way to reach me. So my primary research interest is essentially aligns on microarchitecture and memory system design, like prefetching, cache replacement policies, and other microarchitectural techniques for reducing or tolerating memory access latency, which we are going to cover in this lecture itself. And so we are also focusing on something called like data-driven architectures, right? So essentially, let's say the architectures that are self-learning from the data that it's generating itself, right? Machine learning assisted microarchitectural policies, predictors, how we can improve performance, push the envelope using machine learning techniques in the architecture itself. Okay. So yeah, so in this lecture, this is the kind of the overarching agenda for this lecture. So we are going to have some introduction to the prefetching. We're going to answer some fundamental questions of what exactly is prefetching, why do we need this, when we are going to use it, where to place the prefetching techniques and stuff and like that. And most fundamentally, how exactly prefetching works, right? So that's the fundamentals of prefetching. Then we would do some, basic analysis of prefetching algorithms, how exactly this works, right? And matrix that we use to evaluate a prefetcher. And then we would go for some advanced mechanisms for prefetching. For example, reinforcement learning based prefetching that we have done like a couple of years back, and then run ahead execution that Professor Mutlu has done in his PhD thesis. And still to this date, some advancement of run ahead execution is still going on, and that has been successfully implemented in real processes, as well as people are making improvements on run ahead execution. So we are going to briefly touch upon that. So probably the advanced prefetching lecture that we are going to cover this thing in the next lecture tomorrow. For today, I think if the time permits, then we are going to cover the first 3 points. Okay. So why do we do prefetching, right? So essentially everything stems back to this problem, right? The memory latency problem. And probably you have seen this graph, last, I think some lectures ahead also, some lectures back. So what it essentially says that, in the last couple of decades, right? So we have seen a large increase in the memory capacity as well as the bandwidth, but then the latency is not increasing that much. So it's almost kind of in the same ballpark, like 30% improvement, which is nothing, let's say, as compared to 20x improvement in bandwidth, 128x improvement in capacity, right? So that latency reduction, like slowness of the latency reduction, if we add it on top of today's demanding workloads, right? For example, data center workloads, in-memory data analytics, it essentially creates a cocktail of problem, right? So long memory latency added with a hugely data intensive workload, it creates a main biggest performance bottleneck that we need to solve in today's processor, right? And this paper we have actually shown that in future DRAM directions, it might actually be possible that we would see, let's say, increase in the DRAM latency because of some fundamental scalability reasons, right? So that's also not good for our projections. So essentially what we need to do, we need to design a high performance processor, and that high performance can only come from let's say, latency reduction, latency tolerance, and latency hiding techniques. So what do I mean by each of this? Let's go a bit more detail, right? So there's some error in the animation. Okay, so before going into the prefetching details, right? So I need to just clarify these three things first, right? So we have some techniques that fundamentally reduces latency of the memory. Then we have some techniques that hides the memory from the processor's perspective. So fundamentally, it does not reduce the, let's say, the latency cost of one memory operation, but from the processor's perspective, it hides the latency so that at least processor sees less version of that latency. Okay, and then we have some techniques that essentially tolerates or amortize the latency as seen by the processor. So it does not hide as such, but it let's say amortizes the latency in the sense that you have some independent work that can be done while you are waiting for that memory request to complete. So essentially that's the thing. So we have seen this fundamental approaches that reduces latency from the data-centric approach in the first few lectures, right? In the and memory latency lecture, especially like near data processing and all of these things, they are kind of, let's say, data-centric approach, right? But then the hiding latency and the tolerating latency, they are more on the processor-centric approach. So it's like we are not going to fundamentally reduce the latency, but at least from the processor's perspective, it can go on. The processing can go on while it's waiting for some data to come back. So latency hiding techniques, caching and prefetching are the more prominent ones. And the tolerating technique is what, let's say, out of order execution, multi-threading, and run-ahead execution. Even though run-ahead execution is, let's say, also a type of prefetching techniques, but then it can also be visualized as a latency tolerance technique. So in DDC lecture, we have covered like out of order execution and multi-threading. You know how multi-threading works, right? Virtually every processor that we interact with today, it's kind of, let's say, multi-threaded, right? So you have one process thread, it can actually, get blocked by some memory request, but then some other thread can go on. Or let's say, even if, let's say, all the threads are blocking on the same, let's say, different memory request at once, but then the cost of the latency is getting amortized across all the threads. So that's the concept of multi-threading, right? Out of order execution also kind of goes on to a similar direction. It says that, okay, even in one single thread, even if your processor is waiting on that data to come back, you can actually go ahead and look for independent instructions that can be executed while the processor is waiting for this memory request to come back. So that's the key concept of out of order execution. So for this today's lecture, we are going to focus on, let's say, prefetching. And so that's what I just discussed. And then there are like, lots of let's say, resources that are available online. So if you want to take a look at out of order execution, multi-threading, and caching also, you can just simply follow through these links. Okay. So now let's go into prefetching. And just stop me at any time if you have some question. So what is the idea of prefetching? So the key idea of prefetching is, as the name suggests, right? Prefetch. So it's basically saying that you're going to fetch the data before it's actually needed. Like, for example, let's say you are listening to Spotify music, right? So you're listening to one song, but then before the song finishes, Spotify actually fetches the next song that you might actually listen. So that does what? So if you're on, let's say, a mobile network which does not support high bandwidth connection, so this fetching the next song a bit earlier than your current song finishes, it basically makes your experience seamless. So as long as your first song finishes, you all will automatically go to the second song, right? So it somewhat, let's say, hides the latency of fetching a new song. If it could have waited for the first song to finish, then you would have seen that latency, right? So that's the same exact technique that we are going to use in processor, right? So that's kind of like the analogy, right? So if you have a memory request, that is, when you want to demand it, then only you start fetching it, you would going to see the entirety of the latency, right? But then if you can anticipate that I'm going to use this memory request, let's say, ahead in the future, and fetch that data before the program actually demands it, then that hides the latency, right? So that's the technique here. So why do we do this? Because memory latency is high. I cannot emphasize much. So if you the idea is that if we can prefetch accurately and early enough, as I said, then we can either reduce or completely eliminate this latency from visible from our perspective, right? So it's a processor won't actually see that latency exists. Whenever it demands, it just simply gets it. That's the idea. So it can also eliminate compulsory cache misses in a sense that some requests that you have not seen before, processor has not seen before, it can also predict those requests far ahead, and then it can prefetch those requests inside the cache hierarchy. So that's the compulsory. It can also eliminate the compulsory cache misses, and it can also eliminate capacity, conflict, and coherence cache misses, which we are going to come back later. Okay, so it's evident that prefetching essentially involves that predicting which address is going to be used next. So if I go back to the same analogy, the app, the Spotify app needs to predict that which song that you might actually listen next, right? So that's the case here, right? That you have to predict which address the program might demand next so that you can prefetch. And the hope is that the prefetch is on time, right? So, and of course, it works best if your program have some sort of predictable address pattern, right? So if the program is making some, let's say, irregular accesses, or let's say it's jumping around, right? So then predicting what the program might use next is probably problematic, right? So in that case, prefetching might not work well, but it really works well in case of, let's say, the program that we are seeing has predictable address patterns. Okay, so but then you can think of, I mean, if you have taken, let's say, the digital technique and computer architecture lecture, right? So digital design lecture. So you have seen there is something called branch prediction also. It's also some sort of, let's say, speculative technique, right? So the processor is making some predictions based on what instruction it might fetch next in branch prediction, and it tries to fetch that information before, right? But then that affects the correctness of the program. For example, if you are going to say that, oh, my if clause is going to be not taken and start executing from the else clause, then it's not what actually the program wants to do, right? So that brings us this question that prefetching is also a speculative technique. So that does that mean that prefetching affects the correctness or not? The answer is no. So prefetching does not. That's a good point as compared to, let's say, branch prediction, that prefetching does not affect the correctness of the program execution. It basically says that if you predict something that program is not going to use, you're just doing some, let's say, bogus work. You just fetch the data and you're not using it. So that's wasted in resources, which we are going to look at later, but it's not fundamentally changing the correctness of the program. Because the program eventually demands for some data, it would either get the data in the cache or it won't get the data in the cache. And then in that case, the memory request would finally go out to the main memory or even the slower memory hierarchy, and then you would see the entirety of the latency visible to the processor. But at least the good part is that prefetching does not hamper the correctness of the program. So there is no need for state recovery as compared to the branch prediction problem. And yeah, so that's what I said. As compared to the branch misprediction or value misprediction, we don't have to do any state recovery and stuff. So so that's the basics of the prefetching. As I said, that prefetching is a technique that can reduce both the miss latency and the miss rate of the cache hierarchy. And normally when we do prefetching, prefetching is usually done at cache block level granularity. So it's not going to fetch, let's say, a 8-bit data or let's say a 64-bit data. It's actually going to fetch the entirety of the cache block. So which is typically set at 64 byte. Apple processors, they have like 128 byte cache block. So that might differ from processor to processor. But prefetching normally works at cache block level granularity. So you fetch the entirety of the block. Okay, and so as we go into the deeper into the lecture, right? So we would see that prefetching can be either initiated entirely by hardware. So we as a programmer or let's say the compiler has zero idea of what exactly it's going on. So it's completely transparent to us. Or maybe we can issue some prefetch request by ourselves. We can instruct the compiler to generate prefetch instructions by itself. And then there are some prefetch techniques that can be happening in the system-wide level. Like for example, like operating system can also start let's say loading some data from SSD to your DRAM by anticipating something. For example, let's say Chrome OS has this technique, right? That it can predict that which let's say tabs that you can open, like try to access next. So you have lots of open tabs, right? So Chrome has this predictive capability that, okay, next tab you are going to probably use this. So it can actually start fetching that tabs specific data from the storage, or let's say the compressed memory that it has created beforehand when you use it. So that's like prefetching, as I'm saying like repeatedly, it's a broader concept, right? So people have used it inside processor, people have used it inside operating system, they have used it in networking design, like so many places, right? So essentially the core concept comes back, right? Okay, so this is a kind of like a traditional let's say design where the prefetch resides. So this is a particular example of prefetcher, which is a hardware prefetcher, right? So and also one specific example of the implementation of hardware prefetcher. Let's say in this case, the prefetcher is here just beside the L2 cache, right? So what it sees whatever is coming out of L1I and L1D cache, right? Whatever is missing here, it comes out, and it taps onto that stream. So basically what it does is essentially tries to learn some sort of pattern recognition, right? That, oh, I have seen, and I'll go into those pattern recognition techniques, right? That I have seen cache block A is coming, then A plus 2, then A plus 4, then A plus 6. It essentially realizes that, oh, plus 2 is the stride that, the things are coming from here. So the moment I would see A plus 8, I would actually generate A plus 10 prefetch request, which I would push it here. And that would essentially get pushed into the L2 cache queue. So that's just one implementation, how this looks like in, let's say, real processors. But then that can also vary from, processor to processor design. And as I would show in my like next few slides, right, that there can be, let's say, multiple prefetchers sitting around, the entirety of the cache hierarchy. And in today's processor, we have like lots of prefetcher, not just one prefetcher, multiple prefetcher in the single core running together. So that creates problem, but then it also provides performance benefit. Do we have any question till now? Okay. So let's go in. So here are the 4 basic questions of prefetching, right? So what, when, where, and how. So what means what addresses that you want to prefetch next, right? So that essentially gets dictated by the prediction algorithm itself, right? So the algorithm dictates, it basically learns and tells you what you want to prefetch next. So that's the what. So when part of the story basically says that when do you want to initiate a prefetch request? Like for example, so if I give you an example with that analogy, right? So your current song is not finished yet, but then you want to prefetch the next song. So when exactly is the correct time to start prefetching? Do you wait for, let's say, when the last few seconds of the song remaining, or do you wait for, let's say, almost the last minute is remaining, or do you wait for the last second, right? And as you can guess, like that might depend on what type of data network that you are going in, right? So if your data network is really fast, then you can actually wait for the last few seconds and then start fetching the next song. And it would, by that time, you would have fetched, let's say, a decent chunk of the next song, so that your song transition happens seamlessly, right? But then if you anticipate it wrongly, the user might actually hear a jitter, right? So the current song finishes, and then it waits, there is a buffer, and then the next song starts. So similarly, here in this case also, we have to anticipate it early enough so that by the time the data comes back, processor demands it also on the same time. So ideally, we want it to be exactly on time. Let's say the processor would the prefetch request would fill the data exactly on the same time when the processor is demanding. So if you do it, let's say, way too early, then there might be a chance that you have fetched the data, you have placed the data somewhere, right? And by the time processor is going to demand the data, that data is evicted again. So you basically you were correct at that time. You correctly made a prediction, but you were way too early to even use it. Like by the time the processor actually demands it, it's gone. So that's the problem. The other end of the spectrum is the late prefetch, right? So it basically says that you are again correctly predicted that what the processor is going to demand, but then it's late in a sense that by the time the prefetch has been filled, your processor has already demanded the data. So you cannot, so you did not essentially hide the entirety of the memory access latency, but you have hidden some part of the latency that is overlapping, right? So yeah, but then ideally we want it exactly on time, that it comes in and the processor demands it also. And then there are questions for where. So where has actually multiple questions actually. So like first question is, where do you want to place the prefetch data? Like you're fetching some data, where exactly you want to place, right? So you can place it in the existing cache hierarchy, you can place it in a separate buffer, and we are going to see how exactly these two design space differ. Right? And then there are other questions that we have to also answer, that where do you want to place the prefetcher, right? So as I have shown in this previous slide, right? So in this slide, so we have placed the prefetcher in the beside L2 cache, but then you can also ask that, okay, why don't we place the prefetcher beside the D cache, right? So in that cache. And in today's system, we not only have like 2 levels of cache hierarchy, we have like multiple levels. So then why not there, beside there, right? So that's the where question, right? So where do we want to place the prefetcher? And then there is a third question also, which I'll cover next. And then the final question is like, how does the prefetcher operates? So is it based on software techniques, hardware techniques, execution-based techniques, and so on and so forth. Okay. So yeah. So the remaining part of the lecture is essentially we are going to answer these 4 questions, how exactly they are defined, and then we are going to look for some examples of how these prefetching algorithms work. Okay. Do you have any questions? Okay. Okay. We can take it. I can repeat the question, yeah. Can you repeat that again? Oh yeah, okay. So that's a good question actually. So the question is that, is the memory controller aware of the prefetch request? And I mean, I can actually expand this question even a more like broader aspect, right? That let's say not only just the memory controller, but so if we decide on putting the data into the caches, right? Are the caches aware of that I'm putting the prefetch data, right? So the question is that, is the memory controller or any part of the system is aware of whether it's a prefetch data or whether it's a demand data? So the answer is yes. So we would see right that so if we design some agnostic policies, which is agnostic to agnostic to the fact that whether this memory request is generated by a prefetcher or the memory request is generated by a core, then they tend to perform poorly as compared to a policy that is aware of such decisions, right? So we are going to see such policies, right, in the memory controller as well as in the cache replacement policies, which takes this hints like information into account to make more better decisions, informed decisions. Okay, that's a good question. So okay, so let's go to the first question. So what addresses we want to prefetch, right? So as I said, like if you prefetch something wrong, it's not a problem from the program's correctness perspective, but then it just wastes resources, right? So it wastes resources in the sense it wastes memory bandwidth because you are fetching it, right? It wastes cache or prefetch buffer space wherever you're exactly putting that data, right? So you are wasting that space. You're wasting energy consumption, right? Because fetching this data takes energy. So all of these, let's say, resources which could have otherwise utilized more efficiently by demand requests which are coming from the processor, as well as more accurate prefetch requests. So ideally, we want the prefetcher to have like as high accuracy as possible, right? So accurate predictions are desired, and accuracy we are defining it as this ratio, right? So used prefetches divided by the total number of sent prefetches by the prefetcher. So you can think of, let's say, if the prefetcher is 90% accurate, that means out of all the 100 requests that prefetcher has generated, 90 of them are actually used by the program. So we want it to be as high as possible, but as we would see that normally it's a it's a traditional way of trade-offs, right? So the more you would increase the accuracy, it's highly likely that you would actually lose out on the coverage in the sense like what fraction of the memory requests are actually covered by the prefetchers, right? So we would show this that and there is another metric called timeliness, which we just discussed, right? That how timely that prefetcher is. So these three creates this trio of optimization, and more often than not what we would see that if you optimize, you can get two of them to be in your favor, but highly likely that the other metric would go against your favor, right? So if you optimize for, let's say, coverage, then you would lose out on accuracy. If you optimize for accuracy, maybe you can get better accuracy, better timeliness, but then you would lose out on coverage. So the entirety of the design space ball game here is to make these dynamic decisions, and there has been lots of works. Prefetching has been probably it was let's say initially proposed in 1967. So you can see, let's say, and till today people are they're discovering new algorithms to make better prefetching decisions. So that gives you some sort of indication like how let's say critical these techniques are, and it's going to be even more critical as we go forward into future generation processes, and how seriously system designers take prefetching into consideration when they are designing a new process system, right? So yeah, so as I said, like accuracy is definitely needed, but then how exactly we can achieve that accuracy? So how do we know what to prefetch, right? So so mostly what we are going to see is that if it is let's say hardware based prefetching, which is completely transparent to the compiler, completely transparent to the programmer itself, they predict based on the past access pattern. So basically they tap onto the program's access pattern and then try to do some sort of, let's say, pattern mining, right? And then using those learned patterns, they're essentially going to generate prefetch requests. If we are relying on compilers or programmers' knowledge of data structures, then we can also do it. Either compiler or the programmer can do it by themselves to inject some prefetch request. So that's what how we are going to solve these techniques. But in a sense, prefetching algorithms is what that determines what we are going to prefetch next. Okay, so here is some sort of let's say access pattern and how predictability can be judged from the access pattern, right? So as you can and always keep this in mind that these are like cache block addresses. These are not exact memory addresses, right? So so you're seeing, let's say, a program is accessing a plus 1, a plus 2, a plus 3, a plus 4, and so on and so forth. So you can see, like, it's the easiest way to understand, right, that it's just a streaming pattern. So you're going +1 stride on the positive direction, right? So that's the that's one example. So another example can be, let's say, a bit more complex, but in this case, let's say b plus 42, b plus 84, 126, and so on and so forth. It's still predictable in a sense because it's a arithmetic progression, right? So you have plus 42 stride between two consecutive requests, right? But then life is not always that easy. So we can have, let's say, more complex access patterns like this. So in this case, this is, it might seem a bit more random, but as we will go further, that you can also start, extracting patterns out of this also. And then there are some patterns which are completely, let's say, it just simply seems like irregular, right? But then you can, if you look closely, you can still find some sort of patterns. Let's say, in this case, let's say XYT always, appears together. So there is a high probability that when you see X, it would be followed by Y. When you see X and Y, it would be followed by T. So we have some prefetch, like, pattern learning algorithms that takes this sort of, correlations into consideration. It says that, okay, if I have seen X, there is a high correlation that I'm going to see Y. If I have seen Y, there is a high correlation that I'm going to see T next. And that essentially works, right? So it's like XYT followed by XYT here, followed by XYT here. So as we go, let's say, more complex prefetch design, right? So it would be much more evident that like with more complex design, we can actually cover more sorts of, let's say, pattern recognitions. Okay. So yeah, so that's the what part. When part is basically, it says that, okay, when to initiate a prefetch request. As I said, like if I prefetch too early, the data might actually get evicted from that wherever you have fetched it before the program is going to need it. So that's not good for us. If you prefetch too late, that's also problematic in a sense that you are not going to hide the entirety of the latency. So your certain part of the latency is still exposed, that by the time the data comes back to the processor, your processor has already demanded that data. So too late is also not good. So ideally we want it to be as timely as possible, just on time, let's say. So we have a metric for to define that, which we call the timeliness of the prefetcher. It essentially says that how timely that prefetcher is, in a sense that what fraction of the latency we have hidden, let's say, right? So and we can make any prefetcher timely by making it more aggressive. So let's say by seeing, if I go back to this previous example, right? So by seeing a and a+1, if you're going to prefetch for a+2, then you might be untimely in a sense that by the time the program actually transits to a+2 and then starts demanding for a+2, a+2 might not be actually fetched from the memory. But then if you say that, okay, if I make it more aggressive, I'm saying that, okay, instead of prefetching a+2, you know what, I'm going to prefetch, by seeing a and a+1, I'm going to prefetch a+32, which is probably somewhere here. The idea is that by the time the a+32 is going to be fetched back into the cache hierarchy or prefetch buffer, wherever we want to put it, eventually by that time, the program would actually catch up with the prefetch access stream, and then it would arrive just on time. So if we can make it more aggressive, in a sense that instead of just going for a small look ahead, if you go for a large look ahead, that can actually give you more timeliness. So that's what we are saying here, that prefetch, we can make it more timely by making it more aggressive, as we are going to see that, as I said, like trying to stay ahead of the processor's demand access stream as much as possible. Or if we are going for a softer type of prefetching, then we can actually issue a prefetch instruction way ahead of when it's actually going to be demanded. So we have like a decent gap between the prefetch instruction and the demand instruction that's going to consume, so that it can prefetch just on time. Okay, so that's the that's the when part of the story. And then we have the where part of the story. Where part, it's basically saying, where do we want to place the prefetch data? So we have two options. Either we can place it in cache, or we can place it in prefetch buffer. And then both of them have their own upsides and downsides. If we place it in cache, then it's a simplistic design. You don't have to worry about anything, any new protocols and whatnot. But then the downside is that the fact that you're placing it in the cache, which is already used by the demanded data, you might actually evict something that might be useful. So there is a possibility that you are evicting something which is useful. So that leads to cache pollution. So this is what we call cache pollution. But if you go for a separate prefetch buffer, then so the advantage is that there is no cache pollution, because it's just a separate prefetch buffer, right? So you're not going to pollute the existing cache. But then lots of other questions comes up into the picture, right? That, oh, so where do we want to place this prefetch buffer? How do we want to manage that this prefetch buffer stays coherent with the actual cache, right? How do we size this prefetch buffer? When to access this prefetch buffer? Like lots of questions. So traditionally, all the processes, most of the processes that we see and use, they actually use the prefetching in cache. So basically, they just simply put it inside the cache. But then you can also, there is a legitimate design decisions that can, have a separate prefetch buffer that we can use for, putting the data. Okay. So this is the second question, that which level of the prefetcher, which level of the cache hierarchy we want to place the prefetcher. And as I just said, right, that in modern cache hierarchy, we have like lots of caches, L1, L2, L3, L4 maybe. And then we have like a, huge memory systems also. So where exactly you want to prefetch? So essentially yeah. So basically this boils down to this question that, okay, where do you want to prefetch this data? So do you want to prefetch, so do you want to prefetch this data from, let's say, memory to L2, L4 caches, or do you want to prefetch the data into L1 caches? If you decided to, place it in cache, then which level of the cache you want to place? that actually has its own advantage and disadvantage. Like for example, if you place it in, you might think that, okay, I'm prefetching something from memory all the way up to L1 cache. So the advantage is that it's the fastest cache out there. So if you put it in time, you're definitely going to, when the processor is going to demand the data, it's going to see it in the fastest cache out there, right? So the latency is the slowest possible. But then the disadvantage is that your fastest cache are also the smallest cache. So that there is a more chance of, let's say, pollution if you put it in the faster, let's say L1 cache, as compared to if you put it in, let's say, the bigger but slower L2 or L3 or L4 caches. So there are lots of decision making that needs to happen. So the second, and also, like if you have decided to put the data inside the cache, then the question is that what I just alluded to before, that do you also treat it with the same priority as a demand fetch data, or would you have some sort of, let's say, different priority for these folks? Because you know that these cache blocks that are getting prefetched, they're not actively demanded by the program. So there is a high chance that they might not be even demanded by the program at all. So that's the question that, okay, do you want to place it in the least recently used policy? Do you want to place it as the most recently used? Because depending on how do you prioritize, it also dictates how long it's going to stay inside the cache. So you can say that, okay, I'm going to blindly follow that, okay, my prefetcher is going to be inaccurate as hell. So whatever the data is trying to prefetch, I'm going to deprioritize it and save it in the least recently used place in the cache. But then you might actually ended up, getting less performance benefit, because whatever the prefetch is trying to fetch, it's just getting evicted from the cache, right? So it's like a delicate counterplay between the cache replacement policy as well as the prefetching policy. And there has been lots of research work that has been done and still going on, using machine learning techniques, using non-machine learning, simple, let's say, heuristic-based techniques, how to essentially, balance out this two matrix, like how to essentially co-optimize prefetching in terms of caching and vice versa. So that's what I just said, that, okay, do you want to skew the replacement policy in some way to accommodate this prefetching? Do you want to make the replacement policy prefetch aware or not? That's a bigger question. And then the third question is that where do you want to place the hardware prefetcher? As I just said, that it can be placed anywhere, like it can be placed in L1, L2, and then the more we would go, let's say, deeper into the cache hierarchy, deeper into the memory hierarchy, right? So as you can see, like L1, L2, L3, then main memory, then we have the disk, and then also keep this in mind that main memory can also be, let's say, different types of memories, right? It can be, let's say, DRAM that we all know, live and breathe for, right? But then there can be like newer memory technologies also, right? Like for example, phase change memory, or maybe some newer memory technologies that can come later on future generation of systems. And then in recent times, we have also started seeing this sort of, let's say, like memory hierarchy that are going beyond a certain single node. Like for example, when you are designing a data center class system, right? You're designing the data center for, say, Meta, you are designing data center for Google. So they have like rack scale computations, right? So your memory can literally expand from not just only one node, but it's like a different node, probably sitting somewhere in a different rack also, right? So these memory nodes are essentially connected to the compute node based on some low latency network, but still it's visible from this compute node. So then in that case, how exactly you are going to, let's say, prefetch in those cases. So that's essentially the crux of the problem. And now let's try to look into some sort of, let's say, prefetching algorithms, how exactly the prefetching works, and some techniques. So as I said, like the prefetching can be happening for software prefetching, hardware prefetching, as also execution-based prefetching. So the software-based prefetching is, let's say, what the ISA provides the instruction. So programmer or the compiler is going to insert these instructions explicitly in the program to make these prefetch decisions. Hardware prefetching is especially like you have specialized hardware that generates the memory access automatically, and we as a programmer or the compiler is completely oblivious to this memory request and prefetch request. And then we can have something called the execution-based prefetching, which is essentially, let's say, a execution context, or let's say a thread, right? That is kind of, let's say, running ahead of the actual program execution. just to start fetching the data for the actual execution. So that can again be like a software-based technique, or it can be a hardware-based technique, or it can be a let's say hardware software co-design techniques also. So we are going to look into those tactics also. So let's start with the software-based prefetching. So software-based prefetching, the idea here is, the key idea is simple, that the programmer or the compiler essentially inserts these instructions. So these are ISA instructions, right? So they're not, let's say, you have to explicitly put it inside the binary, and those instructions, they're some sort of, let's say non-returning to the core memory request. It's like you generate a memory request, and the processor does not stop. The processing does not stop. It just simply goes ahead. The memory request would simply come back, and it would just simply fill the cache hierarchy, and that's it. So that's the whole point of this instructions. And as compared to, let's say, a normal load memory request, which is essentially a blocking in a sense that your execution literally needs to wait till the load comes back, and then your subsequent execution can go ahead. But then this software prefetching instruction, they are kind of non-blocking. So essentially they issue this memory request and then they forget. Okay, so that's the idea. So here is an example of, let's say, software prefetching instructions in the Intel not Intel x86 ISA, right? So you can see like 4 software prefetch instructions with different hints. So that's what they call hints, right? So T0 hint, T1, T2, and TA hints. So as you can see, like these instructions, they themselves are kind of let's say like an ISA instruction, but they also have some sort of microarchitecture dependent specification that, oh, where exactly you are going to, if you execute that instruction with that hint, where exactly you are going to place the data. So if you execute this prefetch T0 instruction in Pentium 3 processor, it would place the data in first or second level cache. But if you place it, execute it in Pentium 4, it would place it in the second level cache only. So that's basically dependent on the microarchitecture specification, like who implements and how it implements. So here is an example of, let's say, software prefetching, right? So you have a for loop, and the for loop is essentially iterating over A and B array, right? And just because you know that, okay, you are accessing AI and BI at this iteration, right? So you can actually insert a software prefetch instruction saying that, okay, by the time I'm going to access this, you know what, also start prefetching this address. So A I plus 8 and B I plus 8. So it's going to prefetch this data. And the whole point of these instructions are they are going to fetch this data into the cache hierarchy, and that's it. Okay, so as you can see, like they can work really well for the like a regular array access based address patterns, but then the downsides are that they are instructions, right? So instructions which are flowing through the out of order processor pipeline. So they take up processing and execution bandwidth, and it's also not that easy to determine how early you want to prefetch. Like for example, I'm adding a +8 as a prefetch distance here, right? But then why +8? Why not +16? And that actually depends on, let's say, what is the latency of the memory that you are trying to prefetch, and execution latency also. So it essentially becomes, let's say, the machine dependent. So if you write this code, and this code is, let's say, optimized for, let's say, generation X of the processor, you cannot expect that this same code would be the most optimized version if you change the processor. So that essentially breaks the portability kind of thing. So that's not easy basically to do. And then you also need to have, let's say, these special instructions in the ISA that also makes the ISA a bit more complex. So that's another problem. And then it's also not that easy to do for pointer chasing applications. Like for example, this is a pointer chasing program, right? But then the question is, like, you can either prefetch PRO next, or you can prefetch P3 next, right? So which one is better? It's not easy to answer. So that's the software prefetching in this context, right? So and then you have to also answer this question that, okay, where should a compiler insert prefetch? Like, do you want to prefetch for every load request? Because that might seem good, but then that would also have like too much of bandwidth consumption, like memory bandwidth as well as execution bandwidth. Then you can say that, okay, I'm going to do some sort of profiling and then determine, like, where do you want to put this prefetch instructions, right? So But then the question is like, what if your profiling is wrong, right? So you profiled it with some input set, but then that input is not representative enough. So yeah, so there comes like lots of problem with the software prefetching, but it's also good. It works in some aspects. Let's say if it is regular, memory access stream is very regular, you are accessing an array-like structure, then it's really easy. But then if you're going for, let's say, more irregular kind of workloads, then typically it's not the best choice. So now we are going to look into some hardware prefetching tactics. So I'm going to go a bit faster here, and then yeah, let's cover a couple of these hardware prefetches, and then maybe we can take a short break. So hardware prefetching, as I said, that it's like a specialized hardware. We are not going to initiate this prefetch request from the software. So software is completely agnostic of even understanding that what exactly is happening. So but the prefetch request is automatically getting generated from the hardware itself, right? So idea is the key idea here is that you have a specialized hardware that observes the load or store access patterns and prefetches the data based on their past access behavior. So the trade-offs are essentially like, as compared to the software prefetcher that we have seen, it can be tuned to system implementation. You are not essentially limited to, let's say, optimizing your code for every single hardware that your code is supposed to run. You can just simply take peace in this fact that you have a hardware prefetcher inside that would just simply make your life easier, right? So that's easier. But then it also do not waste the execution bandwidth as compared to the software prefetching. But then there are downsides, saying that you need hardware to detect these patterns, right? And as I said, like these might be challenging, and that's what we are going to show, like how like progressively we are going to build, let's say, how complex these pattern mining algorithms are. Okay, so let's start with something very basic. It's called next line prefetcher. As the name suggests, next line is like when you're going to, the key idea here is that when you are going to see an access to cache line A, you're just going to prefetch some next n line, like A plus 1, A plus 2, A plus 3, up to A plus n. That's the easiest thing. What are the trade-offs? Is the simplest to implement. You're literally not learning anything. You're just simply saying that, oh, if I'm seeing A, then I'm just going to prefetch the next few cache blocks. It surprisingly works well if your program has some sort of sequential and streaming access patterns, but it has downsides. Downsides in the sense, if your program has irregular memory access pattern, then you are screwed. Even if your program have some sort of regular patterns, but not exactly on that streaming way. So let's say, for example, if your stride is 2, so you are accessing A plus 2, A plus 4, but then you're prefetching just the next line. So seeing A, you're prefetching A plus 1. Seeing A plus 2, you're prefetching A plus 3. So you're essentially completely wrong. So you can actually go like really bad in this sort of, let's say, trivial prefetching algorithm, but that's trivial, and that's what we can expect from these algorithms anyway, right? So let's try to make it even a bit better, right? So that's the stride prefetcher. Stride prefetcher essentially says that, oh, you have this sort of access pattern. You can see that there is a arithmetic stride of plus n. So let's try to understand. Let's try to learn. So the idea here is that, okay, record the stride between the consecutive memory accesses. If the strides are stable in the sense you have seen the stride to be repeating. Let's say you have seen n to be repeating once and twice, then you have confidence. Let's go ahead. So that's the idea here. So there are two types of, let's say, stride prefetches based on the exact algorithm that we are going to discuss. So stride determined based on per instruction basis, based on per memory region basis. The core concept is exactly similar. It's just the nuances of the differences of implementation. So let's go to the first one first, the instruction-based stride prefetching. So what does it do? It says that every memory instruction is coming from a instruction pointer, right? So that's what we call the program counter value here. So let's use the program counter to look up into this table. So the table gives you that, saying that, okay, for this PC, you have seen the last address to be this one. Let's say your last address is X, and then your last stride was something N, right? So, and your current address, what's coming in now. So what you do is that you would subtract the current address with the last address that you have seen from the same PC. You would get the stride. If the stride matches with the last stride, you would increase the confidence. And then you have some sort of confidence threshold. You would say that, okay, if I have seen this stride to be repeating, let's say 3 times in a row, then I'm confident enough to say that, okay, this is going to be prefetched next. So that's what happens here. So each load and stored instruction can lead to a memory pattern with a different stride, and that's what we can observe here also. But it can only detect strides that are caused by each instruction. And so, as I said, like if you expect a stride to be repeating across different instructions, then this might not be useful. So that's what we are going to see next. Like that's going to be addressed by this prefetcher, so which is the memory region based prefetcher. So it basically works on the same pattern, right? A plus n, a plus 2n. But instead of indexing this with the cache block, instead of indexing this with the program counter, it actually indexes with the cache block address. So it essentially says that even if these accesses are coming from different instructions, it's still going to learn the stride, and it would simply walk accordingly. Okay. So stream prefetching, especially with the stream buffers, they are as a special case of memory region based stride prefetching with the n value is 1. N value 1 means you're just going to prefetch the next one. Okay. So stride prefetcher, so what are the trade-offs? What are the trade-offs between these two implementation of the stride prefetcher, instruction based and the memory region based? So the instruction based stride prefetcher, so the memory region based stride prefetcher, it can exploit more strides which are appearing if you only look into the memory accesses cross IPs, right? Cross program counters. So they can actually encapsulate the interactions of multiple instructions. The latter can more easily get further ahead, because you can say that, okay, seeing a plus n, I'm going to do a plus 2n, a plus 3n, a plus 4n, because you don't necessarily need the next program counter that's going to use a plus 2n, right? So there is no need for look ahead PC as compared to if you go for the stride, the PC based stride matching algorithm. But then the memory region based stride matching is also hardware expensive, because there are only so many program counters that can be there in your program, but then your data size can be huge, like really huge. So that's the problem here. So we're essentially again coming up to the the trade-offs here. So that's the paper that has like introduced the concept of the program counter based stride prefetching. As you can see, this is from 1991, pretty old. So Intel has some sort of this program IP instruction pointer. They call it instruction pointer, but it's essentially the same program counter thing. So program counter based stride prefetching algorithm inside their products, right? The processors that we use. And this is the paper that has introduced the the stream buffer concept, right? And you can see, like, this is also from 1990s. So that's, yeah, if you're interested, then definitely take a look at it. So I'm going to skip through the stream buffer. If you're interested, then definitely check the paper. So stream buffer is essentially it's a special case of the add memory region based stride prefetching, right? So you have like multiple FIFO queues, but I'm not going to go too much into detail because of the time limits. And yeah, so there is an example of let's say stride prefetcher in IBM Power 4 processor also. This is like one of the early version of multi-core processors, if you don't know. So yeah, I mean they have some innovations, and as you can see, like they have prefetchers across all cache levels. One prefetcher is responsible for fetching from memory to L3. Another guy is fetching from L3 to L2, L2 to L1, and then finally the code demands the data from L1. And each prefetcher is essentially like some front ahead. So if the processor is demanding L0, the prefetcher which is lying here, it's actually fetching the next one. The prefetcher which is lying here, it's fetching the 5 front ahead of L0. And prefetcher which is fetching from memory to L3, it's actually fetching from, let's say, 4 at a bulk and like 17, 18 front ahead, right? So that's like a just to give you an idea of like how exactly these things are implemented in real processors, right? So that's that Norm Jopi paper again for the stream buffers. If you're interested, then definitely check this one. So locality based prefetcher, I'm also going to skip to the locality based prefetcher also. So now let's should we get some sort of quick break, or should we continue? What do you think? Okay. So let's have some break, and then let's meet at 3:40 then. Yeah, that's good. Okay. So let's start from where we just left off, right? So okay, so we are essentially what we are going to do next is we are going to quickly cover some more advanced let's say more complex pattern learning algorithms, right, for prefetching, and then we'll quickly move to how we evaluate a prefetch and exactly, let's say, how these matrices accuracy, coverage, and timeliness interact with each other, right? So, so yeah, so what we have seen till now, it's like simple regular patterns, prefetcher, stride prefetcher, stream prefetcher works really well for them. But then let's say if you have some complex access patterns with, let's say, multiple regular strides, right? So that might not work really well for these, simple pattern learning algorithms, right? And then later on, if you have, let's say, some irregular access patterns, like for example, linked list traversals, indirect accesses, random accesses, it makes your life much harder. So here is an example for, let's say, this workload called GEMS FTTD from Spec, like a well-known benchmark, right? So as you can see, like from an apparent view, it might look into the delta. So delta means the gap between the two consecutive cache line accesses that you're seeing, your program is seeing. So as you can see, like this delta, this graph might look like completely irregular at first, but then if you look closely, that they have some sort of irregularities, right? So, and there are techniques that are bit more complex to learn this sort of, let's say, correlation also. Like for example, this is one paper for path confidence based look ahead prefetching. So the key idea here is that you have given a history or a pattern of strides, a history of strides, then you are going to predict that, okay, what's going to come next. Like for example, in this case, if you see 7, -6, and 12, that is followed by 6. And then similarly, -6, 12, and 6, it's followed by -5, and so on and so forth. So they have some sort of, let's say, prediction confidence mechanism also, that so you seeing this, you predict this with the 85% confidence, so your total overall confidence is 85. Then you also bootstrap this thing, so it says that, okay, now consider this 6 as if it has already appeared by the program. So that makes your history is -6, 12, and 6. Your left shift is this one. Then you predict something with 70% accuracy, your overall accuracy becomes 60%, and then you keep on doing this bootstrapping till, let's say, your overall confidence drops below a threshold. So that's the key idea here, right? So yeah, so as we go along more, let's say, towards let's say more complex address patterns, right? So that essentially gives us this sort of let's say more complex pattern mining algorithms, right? So for example, consider this patterns, right? So in a first glance, again, it might look actually really odd, right? Really, let's say, random at first, right? But if you try to do some sort of, let's say, analysis saying that, okay, whenever I see A, it's highly likely that there is A followed by B here, A followed by B here, and A followed by B here. But then you also have A followed by C, A followed by A. So out of all 6 occurrences, or let's say 5 occurrences, yeah, out of all 5 occurrences, you see A followed by B for 3 times, A followed by A, C 1 times, and A followed by A 1 times. So you can literally create a Markov graph like this. So probably you have known Markov graphs like this, right? So it's like a state transition graph. So you say that, okay, if you see A, there is a 20% probability that the next token would be A, the next address would be A. There would be a 20% probability that the next address would be C, and then there is a 60% probability that your next address would be B. And if you create this sort of Markov table, right? So given a cache block address, what would be your next prefetch candidate, and what is the confidence? The second next prefetch candidate, what is the confidence? If you create this table, that gives you this sort of correlation learning, right? That it basically says that, okay, after seeing an address A, you are likely going to see B with 60% probability, C with 20%, and D with 20% probability. And based on how aggressive your prefetcher is, you can either say that, okay, seeing A, I'm either going to prefetch the most likely one, or maybe I can say that, okay, I would prefetch everything that satisfy this, let's say, minimum threshold. Or you can say that, okay, I'm not only going to predict only one next, I'm going to go a bit deeper. So it's like as if you are going to traverse this graph both in the breadth first manner as well as the depth first manner based on your aggression, right? So if you can create this graph, that can actually give you more, let's say, coverage, and based on how, let's say, aggressive that you want to go, that would actually give you more coverage and benefits. So this one was proposed by in this paper, 1997 ISCA. It's also called Markov prefetcher because of this Markov transition model. So the advantage of this Markov prefetcher is that they can cover arbitrarily, arbitrary access patterns. But then the disadvantages are that these correlation tables can grow arbitrarily large. We would have some, homeworks. You would see that these tables can go arbitrarily large, and that's basically the key limiter of this technique. Another limiter can be that they can have low timeliness. Basically, it says that, okay, seeing A, if you're only going to prefetch A plus, the next one, which is B, let's say, then that's not timely, what we just said, right? How you can improve the timeliness? You can say that, okay, I'm going to make the prefetcher more aggressive. I'm going to say that, okay, not only you have A followed by B, you can also prefetch, let's say, if B followed by D, D followed by F, and so on and so forth. But that also might consume a lot of memory bandwidth based on, and especially when your probabilities are like really low, right? So that creates a problem. And then the third problem is that they cannot actually reduce the compulsory misses. Compulsory misses in the sense, in order to that address to appear anywhere here, you first need to see that address. So it cannot actually predict any prefetch address which it has not seen before. So that's the key fundamental limitation of the correlation-based prefetching. So now let's go to a more sophisticated type of prefetching, which is called content-directed prefetching. I'm just going to quickly cover this one. So as I said, like this is especially targeted for prefetching pointer values, and as we have iterated multiple times, that pointer chasing applications, they are not that hard, like easy to prefetch, right? So here the idea is that, okay, you identify the pointers among all values in a fetch cache block, and then try to issue prefetch requests for them. So, and this was proposed in this paper, a stateless content-directed data prefetching mechanism as first in 2002. And the upside of this technique is that, as the name of the paper says, that there is no table, there is no structure that you have to dedicate for learning things, right? So it's a complete stateless behavior. It can also eliminate compulsory misses as compared to the correlation-based prefetcher that we have seen before. But then the downside is that it can also indiscriminately prefetch all pointers in a cache block. So what do I mean by, let's say, pointers in a cache block? How do you even understand that, oh, the cache block actually has a data value which would be again used as a pointer to fetch the next one? So how to identify the pointer address? So let's try to analyze this. So the key idea here is that so you would compare the address size values within a cache block with the cache block's address. If there is some match in the most significant bit, you would have some sort of confidence that, that value is likely going to be a address itself. So let me show you, like, pictorially what do I mean. So let's say your processor demands this cache block, right? So that cache block with an address of this address. It goes to L2, misses L2, it goes to DRAM, and finally fetches the data from DRAM. It comes back. So that's the address of the cache block. So this is the content of the cache block, okay? So there are 8 chunks of address size value, okay? So now if we decode what exactly, because these things are anyway binary, right? So it would show you the value only how you are going to read it. So we are going to say that, okay, let's break it down to address size chunks, and let's decode what exactly they are saying. So now what we are going to do is we are going to match for each of these values, we are going to match few significant bits and say that, okay, which values are matching those few significant bits, right? So in this case, what happens is that the address of the cache block is matching with the value that is stored over here. So what it essentially says that most likely this value, it itself is a pointer that is going to give you a hint that what the processor is going to fetch next. So what you do, if there is a match, you are essentially going to generate a prefetch request, and then you would just simply follow the same path of the prefetch request. You are going to issue this prefetch, okay? But then the problem here is that how would you, like, if your cache block has like multiple pointers, are you going to fetch for all of them? That's a problem, right? So for example, here we are showing an example, right? So this is like a hash lookup for minimum spanning tree algorithm, right? The graph. And so what it essentially does is that it has a pointer like linked list traversal, and this is the linked list traversal, and for every node it also access, like they have like D1 and D2, right? So, but then the thing is, like, if you look into this function, right, it never touches, it traverses the linked list, but it never touches D2. It barely touches D1 also based on certain conditions. So you can always argue that, okay, in this case, if I just simply run the content directed prefetcher free, it would not only prefetch this guy, not only prefetch the next pointer, but it would also prefetch D1 and D2. But do you need it? Probably the answer is no. So that's what content directed prefetching says, that, here is an example, right? So you have like D1 pointer, D2 pointer, next pointer. If you're going to do the same CDP, it's going to give you match for all this, contents. And essentially, it's going to prefetch all of them. But that's probably problematic. You don't probably need all of them. So then what we can do? So the key idea of this this paper is that you can actually, sorry, where did I go? Okay. So the key idea of the paper is that you're going to profile the program, say that, okay, tell me which nodes are which pointer values are you going to access next, and I'm going to specifically fetch those values. So that's what we're going to happen here. It's basically saying that, okay, the profiling information gives me this fact that, you know what, the next pointer is one that is useful in this context. So prefetch the next one. So I'm going to provide a software hint, and then the hardware essentially would do, saying that, okay, I'm not going to I'm not going to prefetch these pointers. I'm only going to prefetch the key pointers here. So that's the idea here, that even if you would have D1, D2, so there is some wrong in the animation. So even if you have, let's say, D1, D2 and D1, D2 pointer match, but you are only going to prefetch for this next pointers, and that's going to make this content directed prefetcher much more focused, much less aggressive, and it can actually provide performance benefit in more, let's say, resource constrained scenarios. So that's the whole idea of this paper. So if you're interested, definitely check that paper. Okay, so we have like couple of few minutes left. So maybe I would briefly touch down on the prefetcher performance matrix, and then maybe we can start from here in the next lecture also tomorrow. Okay. So when I said like prefetcher performance, so how exactly we measure the performance of a prefetcher? As I said said before also, so this is the trinity of prefetcher performance evaluation, right? So accuracy, coverage, and timeliness. Accuracy defined as this ratio, coverage defined as this, timeliness is defined as this ratio, right? So this is the trinity, but then you also have some other matrices like bandwidth consumption as well as cache pollution, which I have briefly touched upon, right? So bandwidth consumption is essentially saying that, okay, if you're doing a prefetching, then that data is also going to come back from that same bus, right? So that's essentially using that bus. So that's an overhead, right? It might be fine if your data bus is idle to prefetch, but then it might be catastrophic if your data bus is extremely busy. Let's say, for example, if you look into a server processor where you have like lots of cores, but not the memory bandwidth to be sufficient enough for all the cores. In those cases, even if you are correct, we have those examples. Even if you're correct, then you should not probably prefetch. It's better to stay idle as compared to prefetch anything meaningful. And then similarly, like cache pollution is also a problem. So if you have like multiple cores, shared cache across multiple cores, then essentially you're running on the same problem, that if I aggressively prefetch and place it in the cache, then I'm probably evicting some useful data from some other cores, useful data. So that's going to be a problem itself. So yeah, so that's what we are going to try to understand, like how exactly we can let's say tune this performance, right? Tune this, let's say, this trinity as well as the bandwidth consumption and this. So the aggressiveness of a prefetcher is essentially dictates how let's say these three matrices are going to be impacted. So what do we mean by aggressiveness of the prefetcher? Aggressiveness can be encapsulated by these two matrices, prefetch distance and prefetch degree. Okay, so prefetch distance means, let's say, so this is your access stream. This is what the program is accessing. So prefetch distance dictates that if your current demand access is this one, how far ahead you can actually prefetch. So that's the prefetch distance, right? So that's the P max. So you would start prefetching from this guy onwards. Okay, so that's the prefetch distance. You can easily understand that, okay, you can have a conservative distance, you can have a somewhere in the middle of the road distance. You can have somewhere on the very aggressive kind of distance, right? So this is, let's say, in a typical, let's say, stride kind of prefetcher, or let's say stream prefetcher, like how far ahead of the access stream you want to prefetch next. So that's one metric. The second matrix is called prefetch degree. So degree essentially says that seeing next, let's say, cache block access of x to x plus 1, how many you are going to prefetch from this distance. So you have already a distance of this, but then how many of them you are going to prefetch? Are you going to prefetch, in this case, it's a prefetch degree 3. So it basically says I'm going to prefetch 3 next. You can actually have more aggressive saying that, okay, I'm going to prefetch 32 next. You can have more conservative saying that, okay, I'm going to prefetch only 1 and that's it. So based on the aggressiveness, you can actually design. So there is a huge design space of the prefetcher, right? So you can make a very aggressive prefetcher, you can make a very conservative prefetcher, and both of them have their own upsides and downsides. Aggressive prefetcher are more likely to have, let's say, more coverage because they are going more aggressive. They're likely to have more timeliness also, but at the same time, they might waste lots of resources. Like they might waste bandwidth, they might waste cache, they do cache pollutions and so on and so forth. On the other end of the spectrum, if you go for conservative prefetcher, then that is going easy on the pollution side. It's going easy on the bandwidth overhead side. But then you might also lose in terms of let's say coverage. You might lose in terms of timeliness. So as I said, like the entirety of the design space ball game here is always going to be how to manage the balancing act here. So here is an example of what does it mean in terms of performance, right? So as you can see, like if you have no prefetching, very conservative, middle of the road, and very aggressive prefetching, on average, what you can see that, okay, if you make it more aggressive, it's going to improve performance. But then you would see like, workload-wide workloads variations. So in this case, this workload, it's called AMMP, right? It has like 48% performance drop than a no prefetching system if you make it aggressive. So clearly, even if your general trends show that, okay, aggressive prefetching is better in general, but that might not be best in for each workload. So we have this paper called feedback directed prefetching, so which essentially tries to kind of create a decision tree type of algorithm, right? So it says that, okay, I'm going to check accuracy as the first order metric. So if my accuracy is high, let's check the next two metrics. Is it late? Not late. Is it polluting the cache? Is this polluting the cache? Then what do you do? Okay, let's tone down the aggression. So it would decrease the aggressiveness. Is it late? If it is late, then you are going to increase the aggressiveness so that you can be more timely enough. So similarly, you have like different decision trees, and you are going to interact with this implementation in your lab also, which is we are going to release this weekend. So in that lab, you are going to implement and see how exactly these things finally evaluate in terms of performance, right? So as we can see here, if you go for those no prefetching and very aggressive prefetching system, if you see the overall performance, for dynamic prefetching, it's actually improving the performance. And most importantly, if you see those two workloads, right, which were actually taking a performance hit here, but then if you go for dynamic behavior, that actually improves the performance again. So yeah, so that's where I'm going to end it here. So there are lots of work, as I said, like how to manage these prefetchers, right? And then you can actually come up with different types of designs also. Let's say, so we have only touched on the surface, right? So it's like one core, one prefetcher. But then in reality, your systems are not that easy, right? So you would have multiple cores, and each core might have actually multiple prefetchers. Like, so then all of a sudden your design space becomes wide, right? So how would you coordinate the prefetchers in multi-core systems? How would you coordinate prefetch our shared resource managements? And then there are lots of techniques that we can handle in these cases, like memory bandwidth. So this one we have talked about, coordinate control for multiple prefetchers in multi-core systems. Prefetch our shared resource management like memory bandwidth, memory controller managements, and prefetch our DRAM controllers. We got this question from the YouTube, right? So yeah, so essentially what I want to conclude this lecture is saying that this is still an active area of research. So if you can easily think of, let's say, a sophisticated control mechanism that can help us in managing this sort of, let's say, ultra complex demographic, right? So you can think of, let's say, reinforcement learning. You can think of more, let's say, decision tree, random forest based algorithms that can come up with a better, coordination across the different prefetches, across cached, different cores also. So yeah, so that essentially, ends my lecture here. And for tomorrow's lecture, we are going to cover the more advanced sort of prefetching. Let's say we are going to see implementation of RL in prefetching, as well as we are going to cover run-ahead execution. So if we don't have any burning question, then we can conclude the talk. Perfect. So see you tomorrow.